Hello everyone, this is Doug, and in this video we're going to talk about the Friedel crafts alkylation and acylation, which are two more electrophilic aromatic substitutions that we can do on benzene. And what's nice is that they're new ways to make carbon-carbon bonds. So there's two flavors here. They both start with Friedel crafts, but one is an alkylation and one is an acylation. By alkylation, we mean the same thing that we mean every time we say alkyl group, right? We're talking about things that are sp3 hybridized and are just carbons and hydrogens, right? Just an alkyl group. So what we're saying here is that this point here that was attached to the benzene ring, this is an alkyl group, right? So we're gonna have alkylations. We can put on carbon groups. So for example, if I wanna put that isopropyl group on here, I would just use isopropyl chloride or 2-chloropropane. And I'm gonna add actually the same catalyst as I would if I was trying to chlorinate it, this aluminum trichloride. And I'll show you the mechanism here in a second. So we have alkylations. We can put on methyls, isopropyls, T-butyls. We can put on alkyl groups, but we can also put on acyl groups, right? And again, acyl, same thing as we've talked about before. Acyl just means that it starts with a carbonyl. Right, so like this group, this is considered an acyl group because it starts with a carbonyl, right? There's a C double bond O at that point of attachment. It's not sp3 hybridized. It's not just C's and H's. It's a carbonyl, right? So this is a way that we can put ketones basically directly attached to a benzene ring. And I'll show you parts of that mechanism here in a little bit too. So I'm going to show you the mechanisms, and then I'm going to talk about some problems that the Friedel-Crafts alkylation does, and then some of the nice things that Friedel-Crafts acylation can do, how it doesn't have those same sorts of problems. So let's take a look at the mechanism first for our alkylation. So I'm going to redraw this so I can kind of put these together over here. So I'm going to have my isopropyl chloride, right, my 2-chloropropane, and I have my aluminum catalyst. And this first part of this mechanism should look really familiar from that chlorination reaction, where the idea here is that I have really electronegative chlorines, so a partial negative on all those, partial negative on this one over here. And then, so this aluminum is very positive and it doesn't have a full octet. All right, now partial positive on this carbon. But it also that aluminum doesn't have a full octet. And so that chloride from your alkyl halide is able to actually do a Lewis acid-base reaction, add into the aluminum to give us the chlorine attached to the aluminum in the exact same way that we saw the chlorine molecule do in the chlorination. So now that'll become negative, that'll become positive. Now what's going to be different about this is that in those previous reactions, we didn't have the chlorine at the end just pop off. But in this case, right, I'm looking at this and I see that I have a secondary carbon right here. And so I can actually treat this chlorine as like a good leaving group, right? So this chlorine here, it's positive, it wants to take electrons back. This is a secondary spot, so it could, secondary carbocations, those are accessible. And so what we can see is that this chlorine can just leave, right? So the aluminum trichloride is basically helping the chlorine leave, which is going to give us, I'm going to switch sides here just so I can draw attacking my benzene, which gives us the aluminum tetrachloride, which will then spit out one of those chlorides. But I'm not interested in that piece anymore. Now I'm really interested in the fact that I have a secondary carbocation, which, as you can imagine, is a very good nucleophile. Right? This is a very good nucleophile. Or sorry, not nucleophile, electrophile. And that's what we said we needed to produce, right? If I want to do these electrophilic aromatic substitutions, I need to produce really good electrophiles. Carbocations are very good electrophiles. And then the reaction is the same one that I've drawn in all the other videos, where I have my benzene ring. I take one of the pi bonds here. It's going to go and grab your electrophile. You are going to see a series of resonance structures. Right, I can draw these moving over here. Positive there. I don't know. Hopefully you guys can't hear my son being a monkey in the background, but that's just the world we're living in right now. I'll just keep drawing this mechanism. So double bond there, plus there, hydrogen here, isopropyl here. And then the last step, right, is the same, right? So these are resonance structures to each other, right? All resonance structures. And the last step is the same last step where the H falls off to do an E1 type reaction, and then you get your product, right? I drew my isopropyl off to the side, but still it is up there. And then, like all electrophilic aromatic substitution reactions, you have H plus left over, right? Because you replace the hydrogen with whatever the group is. So here's the mechanism for the Friedel-Crafts alkylation. Shares a lot in common, right, with the chlorination here. The difference, though, is that you can make a carbocation, and then the benzene ring attacks that carbocation, and that's when you go through the electrophilic aromatic substitution reaction. Now, Friedel-Crafts alkylation has two problems that you want to be... Actually, it has three problems. It has three problems, and maybe I should try to summarize these at the end here. It has three problems. One is the problem of polyalkylation, right? So poly, we know. Alkylation, we know. Poly just means many. And alkylation, right? We talked about the alkyl groups, right? So I'll just put alkyl groups. Many alkyl groups. Because the idea is that, if I wanted to make this methylbenzene or toluene, the idea is that, I want to put a CH3 on here, so I add CH3Cl. That was what would allow me to do that. But in reality, what you're going to produce is not just that methylbenzene. You're going to get this dimethylbenzene. And if you've already watched the previous videos, that's the para. Or you might get one where there's 3 methyls attached. Right? You might get 3 or 4 or 5. You're going to get many, hence the polyalkylation thing. And the reason that you get polyalkylation is because this product right here is more reactive than the starting material, than just straight up benzene. Right? Here's just straight up benzene. And I know that it is more reactive because I know that CH3s, right, those are weak activators. They're weakly activating groups. So what you did is when you do this reaction, you take whatever your aromatic ring is, in this case it's benzene, and now you've made it weakly activated. So now this is more reactive. Reactions are going to occur more quickly with this than the starting material. So what happens then, right, is that this is then going to react with your CH3, like your next, not next equivalent, but your next adduct where the CH3 and the chlorine attack the aluminum. This is going to react to give you a dimethyl benzene. Well, now we have a new problem here, right? Because now this is more reactive than the thing before, because now it has 2 activating groups on it, and not just 1. So now this is even more reactive. So now this is even more reactive, right? Now this is more reactive than the thing before, the one with just 1 methyl. So then it will react with the same, right? This is the same pot. This is the same pot of reagents here. It will react with more aluminum trichloride and chloromethane to give the tri-substituted product. And I'm going to stop here partly because I'm running out of space, and hopefully you're getting the points here. Now the problem is that this is the most reactive thing in your reaction vessel. All right, now this is the most reactive molecule in your reaction vessel, so now it is going to react, and you're going to get a 4th one on there, and a 5th one. You're just going to get as many as you can fit on there. So we have this problem with polyalkylation. Now I'm going to put in a parentheses over here, kind of on the left, the solution to this problem. The solution to this problem is to dilute your reaction like crazy. So your solution is to dilute, let me clean that up, is to dilute the reaction. Dilute the reaction by using the starting material as the solvent. And that is fine and good. Like for this reaction, that would not be a problem at all because the starting material is benzene, which is sometimes used as a solvent. So, and it's cheap. It's not that big of a deal to add, you know, milliliters and milliliters of this stuff. And then, because you're trying to make a little of that. That's not a big deal. What will become a big deal is when your starting material is more complicated and you've been spending weeks making it, you're not going to use it as a solvent so you can react some small portion of it. And so this is going to become a problem, and I'll show you how to fix this problem in future videos. We'll see that acylating and then reducing it is going to be a better way for us to get at some alkyl groups. So we do have this polyalkylation problem, namely that every time you make a product, that product is more reactive than the starting material. And then you just sort of get this like roller coaster effect, this slippery slope where every new thing you make is even more reactive, and so it just keeps on reacting more and more and more and more. Now the second problem has to do with rearrangements. In theory, right, if I wanted to put on, if I want this group to go on the benzene ring, I just put the chlorine where I want it, right? If I call this carbon 1, 2, 3, and 4, 1, 2, 3, and 4, it's at carbon 2, right? Carbon 2 is where I want it to attach to the benzene ring, so that's where I put the chlorine. The problem is you don't really get this. What you're going to end up getting instead is you're going to get a product where it has rearranged. And when you hear rearrange, I'm guessing you start thinking about carbocations, and that's exactly the problem, right? Remember in this mechanism that you can form carbocations. This aluminum trichloride catalyst is really reactive. It's going to yank those chlorines right off. And so you're going to rearrange. So if you can go from like a less stable carbocation to a more stable carbocation, it's going to happen, right? I won't draw the whole mechanism for this, but you can imagine, right, if I had this chlorine here and I had the AlCl3, it's going to attach here. You have your chlorine now attached to the AlCl3, right? So now that's negative, this is positive. And like we said before, it can pop off. And in this case, it's going to give me a secondary carbocation, and your AlCl4 minus. But what we can see is that this hydrogen at the tertiary spot can migrate on over, just good old hydride shift, or you can see alkyl shifts to give me a tertiary carbocation, which is going to be the most stable thing, which is what the benzene ring ends up attacking and why you see these rearrangements. So you want to keep that in mind too. That's another problem with these alkylations, is that things can rearrange on you, and in fact, they will rearrange on you. Even things like primary alkyl halides are going to rearrange on you, not because necessarily you have a primary carbocation, but because as that aluminum is ripping the chlorine off, something will migrate into it, into that spot. Like there's some good examples in your textbook, but a hydride or an alkyl group will migrate as the chlorine is being pulled off, so that you get these rearrangements and these more stable carbocations, because basically it's the carbocation that is the electrophile that is adding in this Friedel-Crafts alkylation. So that's another thing you want to worry about. And again, I'm going to show you an example at the very end so you can see these rearrangements occurring. So just you want to be mindful of that. Things will rearrange on you. Like an N-butyl, a straight butyl chain, will rearrange into a T-butyl, for example, because that would be the most stable cation you can form. Now the other problem, and I might as well put this here at the bottom. I've got a little room here. So I said problem 2 was rearrangements. Problem 3 is that they cannot work. They're too slow. They're too slow on a strongly deactivated ring, a ring that is already strongly deactivated. I'll say on a ring, yeah, let me say that. On a ring that is already strongly deactivated, on a ring that is already strongly deactivated. So we haven't done any examples yet where we already have things on the ring. We've been just showing plain benzene. But we'll see soon that if I already have a nitro group on that benzene, like if I have nitrobenzene, I cannot do a Friedel-Crafts alkylation because that nitro group is a strong deactivator, and that's going to slow this reaction down so much that we simply don't see the Friedel-Crafts alkylation occur. Same thing if there's already carbonyl on there, same thing if there's already a sulfonic acid on there. Any of those strong deactivators, those strong deactivating groups, these reactions will no longer occur. So polyalkylation has 3 problems. 1, Friedel-Crafts alkylation has 3 problems. One's the polyalkylation, one is that those alkyl groups could rearrange, and the third is that they do not work on rings that are already strongly deactivated. So Friedel-Crafts acylation, how is that similar or different? So let me draw this reagent here. I've got this. And again, my aluminum trichloride. You can imagine that the first step of this is going to be the same thing. Have my chlorine attack into that aluminum. Oops. So negative there, positive there. The aluminum's going to do the same thing where it kind of rips off the chlorine. And you might be thinking, whoa, wait, that doesn't look super duper stable. Because I've just got a positive charge right here right now. And then again, my aluminum tetrachloride. But what's kind of nice about this is that this is resonance stabilized. That lone pair can drop down from that carbonyl and make what's called an acylium ion. Right, because it's like an acyl group, right? It's an acyl group. It's a positive charge on an acyl group. So it's sometimes called acylium ions. But what we are excited about is that these acylium ions, right, are, again, great electrophiles. And when our benzene comes in, our benzene will attack them. And I'm not going to draw the whole mechanism because this video is already getting kind of long, but your benzene would do what it always does, which is go, let me draw it from the other one so that it looks less confusing. I'm going to have my benzene ring go and attack my acylium ion. So I get that intermediate. We have our 2 other resonance structures, and then you lose a hydrogen to get your product. I'm not going to draw it again. You've seen the electrophilic aromatic substitution drawn by me like 4 times or something by now at least. So same thing, and that's how you get your product. One thing else that I want to mention here about the acylium ion, not only is it a great electrophile, but because that carbocation is resonance stabilized, there are no rearrangements. So unlike the alkylation, when you do an acylation, there is not going to be any carbocation rearrangement. The carbocation's there. It's stuck there. It's in the acyl group. That's it. So it doesn't matter if there's a tertiary spot next door or something like that. It's not going to rearrange on you, which solves one of our problems from the alkylation. So speaking of those problems, right? 1, will it polyalkylate? The answer, no. It's not going to polyalkylate. Why is it not going to polyalkylate? Because if you look at this group, right, this group is actually not a weak activating group. This is a strong deactivating group. It's a strong deactivator, which means this reacts slower than the starting material. Right, it's going to react slower than the starting material, so I don't have to worry about a polyacylation. And actually, I shouldn't say polyalkylation, right? It should be polyacylation. But we don't see that. 1 group adds, and that's it. Because as soon as you add 1, that thing is now less reactive. It reacts more slowly than the starting material. So I don't have to worry about that, right? Now, rearrangements, I just said in the previous slide, no, because we don't have a carbocation that can rearrange. We have a carbocation that's caught up in a resonance structure. It's being delocalized. It's already stable enough. It's going to stay there. Nothing is going to migrate into it. So I don't have to worry about rearrangements either, right? So I can have something like, right here, this is a secondary carbon, but over here, this is a tertiary carbon. I don't have to worry about it rearranging or doing anything funny. It's just going to, whatever group I put on in an acylation, that's exactly the group that is going to get put onto the benzene ring, right? We don't have to worry about anything rearranging. But it does have the same third problem. I'm going to add this here. It has the same third problem as the alkylation does. It also does not work on strongly deactivated rings. So if your ring already has a nitro group or a carbonyl or something already on it, it's not going to work. So strongly deactivated, I distracted myself, strongly deactivated rings. We're just going to say no reaction. And what's going to happen is that when we start doing synthesis reactions, we're going to have to start thinking like, okay, if I need to do like a nitration and a Friedel-Crafts alkylation or something like that, I need to do the alkylation first and the nitration second. Because if I do the nitration first, I cannot do the Friedel-Crafts alkylation or acylation. So we're going to see when we start doing synthesis problems that we're going to need to pay attention to this fact. So here's some practice problems. This would be a good place to pause and take a crack at these three. All right, so if I was going to go through them, right, the first one definitely looks like an acylation, so I'm just going to add this whole group right here. So I'm just going to take my benzene ring. It doesn't matter where I put the group. I'm going to put it right here. So 1, 2, 3, 4. So I've got all my pieces. Boom. Did my acylation. Now, in the next one, it's saying, well, what reagents did you add? So it looks like you start here, right, with this plain benzene, and then you get this like 2 benzene groups, but I see that it's connected through a carbonyl. So I can just do an acylation to do that, right? I just need to add this whole thing. So that's exactly what I'm going to do. I'm just going to put a chlorine there, and I'm just going to add the whole piece that I want. I can just do an acylation, and then I'm not going to forget my aluminum trichloride catalyst. Now the next one, it looks like I have butyl chloride or chlorobutane. And this one, you know, I am not going to get what I want because I know this is probably going to rearrange. So maybe I'll get a tiny bit of just butyl, but probably not. What's more likely to happen is that this is going to rearrange into like a T-butyl group. And not only like a T-butyl group, but it's probably going to put on like 2 T-butyl groups. Or maybe I'll get like weird things where I have like something like this and like a T-butyl here and then like a N-butyl here. Like it's just going to be a mess, right? The point is a mess. Not the best way for me to make this butyl benzene, if that's what I'm trying to make. We'll show you better ways to make it in upcoming videos. And then lastly, for this one, I just have a ethyl. Yeah, I just have an ethyl group. I'm just trying to put on CH2, CH3. That can't really rearrange on me. And it says really dilute, like this whole thing is really dilute, so I don't have to worry about polyalkylation then. Probably I'm just trying to make that. And that's okay. I can just say I make that. So here's the Friedel-Crafts alkylations and acylations. Keep in mind the limitations of them. We are going to try to do our best to avoid the Friedel-Crafts alkylations because of so many problems it has and do mostly acylations. But you should do some practice problems. What we're going to see in the next video is that we can take these groups and what's going to happen now if we try to do these reactions if there's something already on the benzene ring. What if I do a Friedel-Crafts acylation and there's already a chlorine on there, or there's already a nitro group on there, or there's already a bromine on there, or there's already another alkyl group there. Like what does that do? Like where do I put the two things? How do these groups direct? So keep an eye out for the next video. It's going to be about directors. Study up. Good luck.